Probably just start. I hope you can hear me.
Yep.
Yes.
If somebody could confirm.
Yes, yes.
Yes.
Do you not hear us?
So can you hear me?
Yes, yes.
Okay, thanks. Sorry. No, I did not hear you, so maybe that's a problem. Can somebody say something?
Hello.
Hello.
Okay, now it worked. Now I hear you. Sorry, I changed my my speaker selections. Okay, so then I just start. Well, good morning, good evening, depending on from where you join. So this is the second lecture on causality after the first one on Tuesday and the practicals yesterday. Well, Elena told me they went well, so I hope you enjoyed it. And well, we definitely have some time today to for you to pose questions at the end or in between, like you want. But I hope we can also, with this lecture, can also answer some of the questions or maybe address some of the points which have been left open on Tuesday or yesterday. Okay, so just to recap from last time, I tried to argue that where scientific data analysis always requires some causal reasoning because data, we cannot interpret data blindly. And then I further argued that causal knowledge or scientific hypotheses are best expressed using causal networks, which is a very basic way and very intuitive way to outline how one thinks that things are related in the real world. And then to extract cause effects from data, what's really relevant is to control for these confounding factors, a term I didn't really specify on Tuesday. But I also mentioned that cause inference really gives these formal rules how to achieve this. And again, I did not specify this in a mathematical sense, but I tried to create some intuition through going to these different examples. The one at this common driver structure where the NAO influenced both Denmark image and precipitation, creating a correlation between the two, but after controlling for it, the correlation vanished. And then we also had the example of the mediator where we tried to quantify the effect of ENSO on California precipitation and saw that when conditioning or when controlling for the mediator jet, actually we regressed out the effect we were interested in. Just to show that statistically these examples were the same, but depending on our causal question, it depends how we have to treat the data, whether we have to condition on a third variable or not. One kind of basic causal structure I left out on Tuesday is this of a common effect, where we have, again, three variables, but in this case, Z is not a common driver, but it's a common effect of X and Y. And I will also talk about this or give an example from climate science today. So what I aim to go through in this lecture is, on the one hand, talking about this last causal structure of a common effect and what happens once we condition on a common effect. And then I will go to talk about controlling for confounders, kind of to quantify causal effects, but do this in a bit more formal or way to, well, go beyond intuition, but really say kind of what rules or kind of what almost, algorithm we can follow, to block the path or to quantify the effect of interest. I will also then give another example from climate science, again, which is a bit more closer to scientific practice, and then finally also go through the one example where we don't use linear regression to quantify causal effects, but instead assume nonlinear dependencies, and then some slides on conclusions, and then hopefully also enough time to ask questions. Okay, to start. So the problem with conditioning on a common effect. Again, we talked about these basic causal structures that have a common driver and the mediator, and as explained on Tuesday, said kind of the implication for the data is that in both cases, the variables X are Y uncorrelated, again, because there's a causal relationship between them, which is indirect. But once we control for that, these are uncorrelated or independent. And I guess this is also something we can really understand intuitively. Then there's also this example of a common effect. And in this case, again, X and Y in this case are uncorrelated, or they're independent statistically speaking, which again makes sense because there's no causal link connecting them. But maybe which is a bit less obvious is that once we control for Z, or once we condition on Z, so the common effect, X and Y actually become correlated. And this is what I try to cover here to show you. Yeah, and maybe to create an intuition, not from climate science, I took this from a paper from Nature Communications, which actually just addresses the issue of conditioning on a common effect, but in the context of COVID. But I like this example. So in this case, imagine where you have an app, like a COVID app, which helps you to track cases, or which gives you a warning once you has to have been exposed by someone who caught COVID. And if you just would analyze the data from this app, you might find that probably younger people are more likely to get COVID. But this causal network here, or this causal graph, if we assume that the age plays a role in whether one uses an app or not, and of course also having a COVID-19 infection also influences whether one uses the app or not. This might actually introduce, or we might find that younger people are more likely to get COVID, but just because we just use the sample of people using the app. And again, so that we get this correlation between age and COVID-19 infection, but just because we have this, we used a sample, or we selected a sample, which is not really representative, but it actually is this common effect of the two. Yeah, maybe this already gives you some, again, intuition, but now I will go through an example from climate science. Actually, let's say, or going back, we first thought that such a case that conditioning on a common effect is maybe not such a problem in climate science, because we usually, oh, sorry, it's in the chat. Yeah, sampling bias is another way to express this. Thanks, Dad. So because usually, let's say we are more interested in drivers, let's say in the context of climate teleconnection, we are probably more interested in the drivers, and the common effect would be something like maybe a region variable, or like an extreme event or drought in a particular region. But here's an example from climate science. So again, this is looking at the stratospheric polar vortex. We had this in the previous examples, but again, this is the polar vortex, or the SPV, how I call it, is this band of fast westerly winds, which forms in winter. In this case, it's the northern hemisphere SPV, but the southern hemisphere has also one. And the plot on the right, this is using data from a seasonal forecasting model. This shows how the winds in the stratosphere, at 10 hectopascal in this case, how they change over the course of the winter. So if you focus on this thin black line, which indicates the mean, this shows the mean strength of this polar vortex. So we usually have these strong westerly, so positive winds in the stratosphere, so around 30 meters per second. They in winter they are strongest, and then in spring, so in March, April, you see that the winds get weaker, and at some point even become they become negative, meaning that the vortex has breakdown. So we care about the polar vortex because it can affect also the circulation in the troposphere. For example, again, using a causal network to express this knowledge, the polar vortex in the stratosphere influences the strength of North Atlantic oscillation. And again, this is important for weather and climate in Europe. And to show you this again, this is using the same data. This is the scatter plot of the polar vortex anomalies in the North Atlantic, or the NAO anomalies, where it looks like a cloud, but actually there's the correlation of 0.24. Well, it varies a bit depending how you define the polar vortex and the NAO. But so there is, like, if the polar vortex is strong, we usually have a positive phase of the NAO, or more positive phase of the NAO. If it's weak, we usually we tend to see also more negative phases of this North Atlantic oscillation. So, but usually we care about a particular aspect of the polar vortex, so-called sudden stratospheric warmings. These are the very extreme cases of the polar vortex, and this is basically the days when the winds turn negative. Looking again at this plot, well, the thin line represents the mean, but the gray shadings indicates the 1 and 2 standard deviations. So yeah, basically variability. And you see that usually the winds are positive, so we have positive values, but sometimes the winds also become negative already in winter. So if you look at the gray shading, or let me use the mouse here. So in this case, is the vortex, there was a breakdown of the vortex or very strong warming in the stratosphere. In this case, is the winds reverse. And these days are defined as sudden stratospheric warmings. And again, these are these examples of these very extreme weak states of the polar vortex, which we again know then tend to see this negative phase of the North Atlantic oscillation. So we can basically expand the network in this case and also include these SSWs. What we found in a paper led by Eric Camonon was that actually when we look at the seasonality of the impacts of these SSWs, we see differences for the different winter months. This plot shows the temperature anomalies following SSWs, but this time split by the month of occurrence. And well, the pattern we see is always the same. So we have cold anomalies in Northern Europe and warmer temperature anomalies in Southern Europe. But you can also see that the anomalies are much more pronounced in early winter, so in December and January compared to late winter. And this is something we didn't understand right away. But what happened actually was, well, that we conditioned on a collide or on a common effect, as I will explain. So again, going back to this definition of SSWs, you can see again that we have this mean state, which decreases over the course of the winter, whereas variability is more or less the same. But this also means to be classified as a SSW, you need stronger wind anomalies in the stratospheres in early winter, just like to go below the zero line, compared to events which occur in March, where the mean state is weaker in the stratosphere or of the polar vortex, meaning that to turn for a day to be classified as SSW or so with negative winds, the anomaly in the stratosphere is usually lower. And actually this kind of difference completely explains the differences we saw in the response. So in this case, you see the polar vortex anomaly on the x-axis, and again the NAO anomaly on the y-axis, and the different squares here show the average over all the events, but for the different winter months, and we always see this perfect correlation. So meaning that just we can understand that if the forcing is strong in the stratosphere, also the response in the troposphere, so for example in the NAO, is stronger. But then again, it's just the result of, or the stronger forcing is just the result of these early winter SSWs being associated with stronger wind anomalies due to the definition of an SSW, which includes this absolute threshold. Expressed in a graph, we actually have another node, which is month. So in this case, the month also affects whether a day is classified as an SSW or not. So in this case, by conditioning on the common effect SSW, or by conditioning, I mean just considering these extreme SSW cases, we introduced this non-causal association between the anomaly in the stratosphere and the month, which again, usually we would not expect to occur because also, variability is the same over the course of the winter. You can also express this just using data to give you hopefully more intuition. So this shows again this plot from the beginning where we have the SPV anomaly on the x-axis and the NAO anomaly on the y-axis, and the different dots, the colored different dots represent the different winter months. So the bluish one is early winter and the yellow and orange is the late winter month. And you see, well, the dots there's no structure in the color. So usually the anomaly and the month, there's no relationship, again, as we would expect. But once we only consider the SSW, so these extreme cases, we now see this relationship between polar vortex anomaly and the month. So with the early month being more on the left, the early winter SSWs showing these stronger anomalies compared to the late winter SSWs. And again, this is just the result of the definition of an SSW. All right, so again, this now, now we basically conclude these three causal structures. So we're going to now go on and talk a bit more in detail about controlling for confounders, what this means, or to give you some more basically formal rules how to do this. I wrote here in a nutshell because, of course, it's a more, well, it's I try to not be too heavy on the mathematics, but again, try to do this a bit more formal way. But again, it's in the nutshell, so it's not always 100% mathematically precise, but I will also give you some more references. But again, what I'm trying to achieve here is to create some intuition of how we can control for confounding factors. To do this, some more notes on causal networks. So recall that we express our hypothesis using causal networks, and these consist of these nodes, which represent different, there's a typo, variables. For example, we can think of ENSO on the NAO. And then we have these links, which indicate the direction of causality. The mathematical term for causal networks actually directed as cyclic graph. So graph is just the mathematical term for network. And directed, we mean that the arrows point in one direction. So so we have forward or backward pointing arrows. And acyclic means that there are no causal loops allowed. So you cannot go from X and then through the network and then end at X again. Another term we now need is this term of a path in the network or on the graph. And so we call this, like we have a sequence of links which connects two nodes of the network, we call this a path. And in this case, it's important to remember this is regardless of the direction of the arrow. So it's a bit confusing in terms of terms, because when we talk about teleconnection, we also talk about pathways. In this case, there is a direction involved, but in the mathematical sense, or in this context of DEX or causal networks, a path is just connecting two nodes in the network. In this case, for example, if we look at the path from X to Y in this network, there's one path which is basically the causal one, which connects X and Y, so it goes through U. So we have a link from X to U and then to Y. But there's also another path connecting X and Y, which goes through Z. Again, in this case, there is a common driver, but it's not about, again, the direction of causality. It's really just about, is there a path in the network where we can go from X to Y? And so when we think about these basic causal structures, for example, a common driver and a mediator, we can also, when we think about this as path, there's this term open, which we now need. And we said that the path, and in both cases, there's a path from X to Y, so there's a link from them from one to the other. And in these cases, we say that they're open. So this is using this kind of network intuition. Before we just said they are dependent, or there's a correlation or association between them. But we can basically translate this into network terms, and it's the same as saying there's an open path between them. Similarly, we say they are independent conditional on Z, or using this graph or network terminology, we say the path from X to Y is blocked by conditioning on Z. So it's basically using the same thing, but now we want to use this network intuition, which is really graphical, so we can see where information is flowing and where we expect correlations. And now in the case of the common effect, it's the other way around. We say that we know that they are actually independent, or there's no correlation between them. And using network language, we know that, or we say that a path from X to Y is blocked by this common effect Z. And the same, we open this path from X to Y once we're conditioning on this common effect Z. All right, so again, this example we had before, the common driver, we had this open path from Denmark to Mediterranean through NAO. And again, so that we had this correlation between them, and we conditioned on the NAO to block this path and found them to be independent. And the same with this mediating example, there's this, if you just look at the path in the network, there's this path from ENSO to California via JET, and by conditioning on JET, we block this path. And then the last example, we had a path from the polar vortex to MANS through SSW. Again, if there's a collider in the network, then the path is actually blocked. But by conditioning on it, we could open this path. And again, there's actually like mathematical rules to really, which of this do calculus, because remember again, we're interested in causal effects. So we were interested in this interventional condition distribution to quantify the causal effect of X on Y, so the probability of Y after doing X. But again, we cannot compute this. So basically the aim is to express this interventional condition probability such that it contains no do expressions anymore, because the only thing we can compute from data is observational condition probabilities, because we are not making these interventions. We are actually not making these interventions. And then at Judah Pearl and others, they really provided these three simple rules of do calculus, where you basically can play around with the condition probabilities. And there are three basic rules. I just quickly go through them. The first rule is basically saying, or giving you a rule when to decide if we can ignore an observation. So in this case, you see the W is left out, and you can do this if this W is irrelevant to Y in the network. The second rule is to decide if we can treat an intervention as an observation. So this is kind of the important one. So when we can kind of leave out the do X and estimate it purely based on observational data. And the third one is also if we can ignore an intervention and just leave out the do X. Again, this is basically, from a mathematical point of view, everything one needs to then decide whether one can calculate this do expression just using conditional or observational data.
Marlene, we have a question from Sahil.
Yes, sorry.
He's just asking to explain the lingo, closing the path and opening the path. I don't know if you want to just go back to that quickly.
Yeah, sure. So again, so a path is everything. A path is everything which connects two nodes in a network. And oh, sorry, my mouse is striking. So a path is everything which connects two nodes in a network. I hope this was clear. Again, regardless of the direction of causality. And then we say, and this is in this slide, we say if we have a common driver or a mediator, we say that the path is open, because you have this kind of, again, for the intuition in this case, the path is open, meaning there's a correlation or there's some dependence by it, which is the case if we have this mediating effect, or once we have a common driver. So in these two cases, the path is open. In the case of a common effect, the path is closed. So there is no flow of information from X to Y. It collides in the common effect. But it's important to remember then, once we condition or once we control a third variable, for example, in the case of multiple linear regression, we actually we block the pathway, or we block the path in the first two cases, but we open it in the third case. So it's really just understanding these two paths are open here from X to Y. This path from X to Y is closed by the collider, and then on the common effect. And by conditioning on the third variable Z, we block the path in the first two examples, and we open it in the third case. But well, no worries. I think it will become more clear in the next slide.
Loritz has just asked if it means it's correlated or not, and that's without conditioning that would be true, right?
Yes. So again, so basically, open means it's correlated or there's an association. When it's closed, like in this case, it means there's no correlation. The same case, conditioning on Z means the path is closed, there's no more correlation, like in this NAO example. So now the path is open, so we find a correlation between these two. Once we control for the NAO, we block the path from Denmark to Mediterranean, meaning there's no more association. So it's basically just, the one is the kind of you can do with data, the other one is just giving an intuition just by looking at the network. And this again, hopefully shows the power of causal networks, which is so simple, but it, you can easily trace where you expected to find a correlation, where not. And again, it's just, you just have to know these three causal structures. Okay, to go on. So there are these mathematical rules, but we ignore them for the time being. We just focus on the so-called vector criterion, which follows from these three rules of do calculus. But it's really a heuristic, or it's just another rule, which is just very graphical and very well, easy to understand. So it basically says, and again, it's not the most precise mathematical language, but again, to understand the rule, it's to quantify the cause effect of X on Y. All one needs to do is to control for all the confounding factors. So again, confounding factors, what I mean by this is that actually anything that leads to the conditional, this observational condition probability being different from this intervention probability we're interested in. So again, the idea is that the effect is somewhere in the condition probability. So for example, in the correlation, but we have to control for these factors which bias or which kind of introduce a bias. And then in network language, we can translate this to say to quantify the effect of X on Y, we need to block all the open path between them. Other, of course, the one than the one of we're actually interested in measuring. And I will give some examples, and I hope and I think it will be clear then. So let's start with this, the very basic example of which is like how an example of a good control. I will also give some examples again which are bad controls. So in this case, again, we in all these cases I'm showing now we're interested in quantifying the effect of X on Y. And I show or and we condition on this red dot or this red node here Z. So in this case, we want to quantify this effect. This is kind of the cause or the open path we want to quantify, but there's this other open path connecting X and Y, which goes through Z. So to quantify the effect here, we have to control on Z, because this will block this other open path, this backdoor path, which is also called connecting the two, but which kind of is not the causal one we're interested in. In a similar way, we can also, there could also be a common driver, Z, and in this case, we have the same effect. So we want to quantify the effect from X on Y. There is this backdoor path connecting them, which we want to close or to block. And we can do this just by blocking on Z, because in this case, we blocked this pathway or this path, sorry. Another example is this one here, where we have a mediator between X and Y. So, so in this case, the common cause of X and the mediator between X and Y, this is also a confounding effect, or confounds the effect of X and Y. So in this case, again, by blocking, or so by controlling on Z, or conditioning on Z, in network thinking, it will block the open path connecting X and Y, which other one the one we're interested in. The same here, we also include a mediator, so it's basically the same examples as before, but just to think that the common effect of a mediator makes also we also have to control for. Yeah, so again, we can just think of this confounding factor basically as a common driver, but of course, sometimes the causal network structures can be a bit more complicated. Well, examples of bad controls is this one again. Again, we're interested in quantifying the effect of X and Y. Imagine that we would condition it on Z here, or control for Z. What this means is that actually we had this the path from, there is a path, another path from X to Y, but you can see that Z is a common effect of U1 and U2. And again, I said that we know that in a common effect, the path is already blocked. So there is no path, there's no open path, but only blocked one. So by conditioning on Z, we would actually open this path from X to Y, therefore actually introducing a bias, so making things worse. So in this case, we should not control for Z. Another example is this one, of course. This is the same from the jet example. Again, we have this open path. Once we control on Z, we actually block the path, so we are no more measuring the effect of X on Y. And this is this could also be the case if we have a mediator, X and Y. In this case, so Z is not that we also call this a descendant of M, but in this case, blocking or controlling for Z is also actually causing a problem, because it will also partially block the path from X to Y through M. And I think this also makes intuitively sense, because of course the Z is you can think of this as some evidence for M. So if you know Z, you have knowledge of M, So by conditioning on that, you would also partially kind of block or control away the influence for X and Y one is interested in. And actually, you can really recommend this blog post, or there's also a paper on this, but really goes through very these examples of good and bad controls. And I think this is quite useful. But again, the basic idea, or the spectral criterion is really, all you need, or often all you need to do is really just to see where's my my pathway of interest, or my path of interest, so the causal one from X to Y, and which are all the other ones which connect X and Y, which are also open, meaning there's no collider, no common effect involved. And then just condition on these, or control for these, to block these paths. So this is why causal networks are so powerful, because they really give you this graphical intuition where information is flowing, or where correlation is expected, and how you can control for it. Again, also to mention again, this was really a very basic introduction to the Stoop calculus and the vector criterion. Again, I can recommend these 3 books by Julia Pearl. The one on the left is more this popular book, but where also these concepts are explained. The one in the middle is, I think, a very nice starting point. This is a primer, so it involves more equations, but really on a basic level. And the one on the right is really summarizing everything. So I don't think it's a good read to start with. So, but the 2 on the left, I think I can really recommend. And then there are really many tutorials on the internet. If you're interested, I can also forward you some links, the ones I found useful. But I think where you can find one which best captures or gives you the best intuition. Okay, now back to climate science example. The examples I showed before, with using the NAO and the jet stream, they're really simple. They just involve 3 variables. The numbers added up nicely. We didn't include any lags, time lags. So this case, I tried to give you one example, which I think shows better actually why causal networks are so powerful, or why they're really useful for climate science. But it also shows some of the challenges we deal with, because the assumption of no causal loops, so that of the graph being acyclic, this is of course something which is not really, or basically never fulfilled when we talk about a physical system like the Earth system, where everything is connected. But I tried to give you one example where I think we can try to overcome this limitation. So again, talking about the polar vortex, but in this case, the kind of the question we addressed in this one paper is that we were asking how strong is the effect of Barents-Sankara sea ice, so sea ice, roughly in this region, is in autumn, is on the polar vortex, again, the polar vortex being strongest in winter. And the reason is that there's really a huge scientific debate behind this, whether sea ice loss in the Arctic, which is of course an indication of climate change, whether or how this affects weather in the mid-latitudes. And there's one hypothesis that sea ice loss in this area affects leads to a weakening of the polar vortex. And then again, like shown before, a weak polar vortex leads to a more negative NAO-like weather situations. So understanding whether sea ice loss really causes or contributes to more extreme weather in Europe is of course important to understand. But there's a huge debate because quantifying this effect from data is difficult. And at the same time, the climate model experiments, they really give or partly give different results. So again, inferring causality or quantifying this cause effect is something we're interested in, but which we cannot really decide. And we try to kind of address this issue using methods from causal inference. So again, to start this, obviously, like you now know after these lectures, is to start with the causal network. And in this case, the challenge is really to include all the potential confounding factors which make it so difficult to quantify the effect from Barents-Sankara sea ice to the polar vortex. So the causal pathway we are first of all interested in is that the Barents-Sankara sea ice affects sea level pressure anomalies in the Ural Mountain region, so leading to kind of a more high pressure system there. and this then influences the polar vortex. So this is the pathway we want to measure. But then again, there are different confounding factors. For example, the Aleutian low is known to also affect the strength of the polar vortex, but it can also affect North Atlantic circulation, and thereby also sea ice conditions in the Arctic, the Atlantic part of the Arctic. So we have this common driver Aleutian low. And actually also there are different other common drivers like El Niño Southern Oscillation or the Madden-Green Oscillation, MJO, but these are assumed to be mediated by the Aleutian low. So so these tropical drivers are also expected to affect the Aleutian low, and again, this is then this common driver. And
Marlene,
then
we've got another question. Is it possible to include bidirectional effects and feedback mechanisms in the causal framework?
Yeah, they're actually covered in this example. So maybe let me know after this example if this is
very good.
Yeah, if I should come back to the question. Thanks. Okay, because now the tricky things comes, and like I said, in the climate system we have feedbacks, and this makes things usually difficult. And in this case in particular, we also know that high pressure over the Ural Mountains, they also affect sea ice conditions. And so now again in this case we have a feedback. And again, this is usually, actually there's also a mathematical way to how to address this, or a different way. So going beyond these very simple rules, there's also rich literature on feedbacks and so on. But I think in this case, all we need to know is, we have to think about or make use of the fact that there are time lags involved between cause and effect, and which we can of course also model with our data. Okay, so let's say this is the graph, and we're interested in quantifying this this dashed path in the network. But we have these different problems. So first of all, I think or maybe I'll say this afterwards. So again, if we we have our causal model, so we think this is kind of a plausible way to illustrate or to summarize the different causal pathways in the climate system, which might bias our, or which might affect the way we quantify the effect of Barents-Kara sea ice on the polar vortex purely based on data. So now we can think of the vector criterion, or we can think of, okay, how can we now extract this pathway from the data? So we're interested, or there's one open path from Barents-Kara to the polar vortex, which is the one we want to measure. So this is the one which from Barents-Kara sea ice in autumn to the polar vortex in winter. So this is this one. So, and again, we assume linearity. So we think multiple linear regression is a good way, or linear regression is a good way to quantify this potentially linear dependencies. So in the end, we want something like the polar vortex in winter, so January, February, March, and express this as a function of Barents-Kara sea ice in autumn, October, November, December. So we're interested in quantifying this regression coefficient A. But again, this is something we can compute, but we have to control for these confounding factors, meaning we have to close all the other open paths connecting Barents-Kara sea ice and SPV in this network. So now let's go through this. So on the one hand, we have an open path connecting the two, which goes from Barents-Kara sea ice to the Aleutian low to the polar vortex. So we have this common driver. We of course also have these other common drivers, but again, they're mediated by Aleutian low. We also already know that conditioning then on this mediating factor is enough. But sorry, back to the example. So we have this open path connecting them via Aleutian low. So we have to block this. We have to close this open path, and how can we block, or how can we close this path? This is just by conditioning on the Aleutian low, which in the case of using linear regression simply means including the variable in our linear regression model. So we further include Aleutian low. Sorry, I lost my mouse again. And I'm also taking here the month October, November, December to make sure, which is the same as the effect. So make sure that or it could also be earlier variables, but of course it shouldn't be later than October, November, December, because we know that the cause has to come before the effect. But now comes the tricky part. So we also know we have this, well, which seems like a loop, but we have this path from connecting Benson-Caraccias and the polar vortex via Ural, but in this case, Ural is a common driver of the polar vortex. And this is now we're in this tricky situation that on the one hand, we have to control for Ural. This is what we know when we have a common driver, we have to block this open path. But at the same time, Ural is also a mediator, and this is the causal path we are interested in measuring. And this is something where we have this kind of feedback or loop situation, and this is of course something we deal a lot with in scientific practice. But let's say just at least in this case, or this is maybe not an assumption which is always valid, but in our case, we can make use of. So sorry, this is the same. So we want to block this path, but in this case, we don't want to block the mediating part of Ural. So what we did here is to make use of this involved time lag. So in this case, we included also Ural in October, November, December in the regression model, meaning that we blocked the path, or we closed the open path of this common driver Ural. But what this means is that all the effect of Ural in October, November, December is regressed out or controlled for, because we believe that, or we assume that the mediating part of Ural actually involves some time lag, so happens after October, November, December. So in this case, we control away everything happening in October, November, December, but everything happening between October, November, December, and January, February, March, which is our variable of the polar vortex, this is still involved. This is not controlled for. So I hope this makes sense in a way that we kind of overcome this issue of the feedback loop just by looking at the network by using variables of different time lags. In a way, we could also have drawn two nodes of Ural, one in October, November, December, and the other one, for example, in December, January, February, or January, February, March, to make this clear. And again, this might not always work, but in the case of teleconnections, where we have some longer time lags available, I think we can. It's often an assumption we can make to just consider the different time lags. But I think what this example shows in general is that on the one hand, if we want to quantify an effect from data, and there are different mechanisms which likely confound the analysis, we have to make our assumptions really explicit, and causal networks are really a way to make them, or help you to make them explicit. At the same time, they also help you to identify where information is propagating, and where the open path or the dependency you want to regress out. Because once you do this, so once you apply basically this vector criterion, what we can do is we can interpret this regression coefficient as the causal effect, again, conditional on this causal network. So saying that if we agree that this causal network kind of represents some reduced version of the truth of the climate system, and after we control for these confounding factors, we are in a way we can present, or we make sense to interpret this regression coefficient A as the causal effect of Benson-Caraccias on the polar vortex. Again, we cannot just do this just by correlating the two, or by just computing the regression of, or by regressing the polar vortex SPV on Benson-Caraccias. But in this case, we did control for the confounders, meaning we blocked the open path in the network other than the path of interest. Okay, so I have a few minutes left, and I will just want to give one example of quantifying nonlinear dependencies, because so far all we used was multiple linear regression because it's easy to explain. But again, the causal network approach is fully non-parametric, meaning that whether you take a linear, whether you assume linearity and use linear regression is up to you as a researcher, but you can also, of course, quantify nonlinear dependencies. There are different ways to do this, and I will here go through one example. Here we again in the southern hemisphere, so we have precipitation in Australia, which is known to be affected again by ENSO, so any southern oscillation, but also by the Indian Ocean dipole IOD. And well, this network structure, we already had this in the previous lecture, so we have this indirect and this direct pathway of ENSO. But there are different papers indicating that this relationship likely involves nonlinearity. So in this case, it makes no sense to use linear regression if we are interested in nonlinear relationships. So what we do to kind of talk about this or to quantify probabilities is that we stratify the data into different categories, which also makes sense from a physical point of view. So for Australia, we include below and above average precipitation, these two categories. For the IOD, it's common to use negative, neutral, and positive phases. So we split it in tercites, and we do the same for ENSO, which gives us the three categories of La Nina, neutral, and El Nino conditions. And then we can express these dependencies in a table, which gives the condition probabilities, in this case only showing the ones for above average Australian precipitation. So by default, we would expect a probability of 1/2, so 0.5 for above average precipitation. But we can now quantify how this looks for the different combinations of seeing different ENSO or IOD conditions. For below average precipitation, of course, it's just the deviation from 1. So we see this table. We also have our marginal probabilities. But again, how we interpret the data, it really again depends on how we think what is the common driver, whether it's ENSO or the IOD, like we talked in the previous example. But just to give 2 examples, so for example, we could be interested in or we can see the association of El Nino and above average precipitation. And for example, you can see, or you can read off from this table that the probability of having above average precipitation during an El Nino event is 0.22, which again is much lower than the default probability of 0.5. So it's more unlikely to see above average precipitation. In contrast, if we have the above average precipitation is more likely during a negative phase of the IOD, where we see a probability of 0.67, so higher than the default probability. We can also answer more interesting questions for something like, what is the added information provided by the Indian Ocean dipole, given that we already know ENSO, and then again expressed as in condition probabilities. This is this, so we have the probability of above average precipitation in Australia, given IOD plus and El Nino, for instance, and we can read this off the table, which gives a probability of 0.24. We can compute the same without accounting for or stratifying the different IOD phases, just only computing it and having the knowledge of El Nino. In this case, we get 0.22. So you see, the ratio of the two is 0.9. That really, additionally, knowing that IOD is in a positive phase really gives, increases the chance of only 9%. So the knowledge of knowing ENSO, the ENSO state, is already, contributes a lot to knowing the state of Australian precipitation. I'm not showing the data here, but this also follows just really from the joint probability of ENSO and the IOD, where the IOD phase really is determined a lot by the phase of ENSO, where there's a high correlation of occurrences of the different combinations. Well, the first point again is here that, of course, we in this case we didn't use any linear regression, but still we quantified these conditional probabilities using this this method of stratifying the data. And again, it's really important to see that really again the interpretation of the data depends on these causal assumptions. How we interpret them depends on the network, the second point is, again, we have just a simple example where we have only 3 variables, and for Australia we only have 2 categories. So might be easy. It might be possible to make sense of the data without any causal network and just having this intuition in mind. But in the situation, like remember the case of the Arctic example, where you have different nodes and different links. If you then compute condition probability tables, I think it's really easy to get lost and to be confused with any causal interpretations if you don't have a causal network at hand where you can go through the numbers and can understand where information is propagating, how this condition probabilities add up to also decompose the different causal effects. Okay, so I'm at the end of the lecture, and I'll try to make some more general conclusions. So again, I showed this in the first lecture, but I think I hope after this lecture, this makes even more sense now. So again, in causal inference, if we're interested in quantifying a causal effect of X on Y, the very first step is really to draw your hypotheses, to use your knowledge to set a plausible causal model if you think how things are related. The second step, you then look at your data and see whether this is consistent with this network structure. And in particular, if you're interested in expressing or in quantifying a causal effect, so predict the effect of an intervention, you have to control for the confounding factors. And again, this is everything that leads to this observational conditional probability being different from this interventional conditional probability. And this backdoor criterion is a very simple heuristic to understand which path in the network you have to control for. Again, in this case, we have to block this open path from X to Y, which goes through Z. And then again, in the linear case, that is as easy as including Z in the linear regression model. But one can also do this, of course, with other things as using stratified data, as shown in the previous example. So what I try to argue, over the course of both lectures, is that really that scientific data science or data analysis is never really objective, like we often claim, especially when we use, for example, cluster algorithms or other machine learning tools. There's always some assumptions involved and some knowledge enters the way we analyze the data. So I think it's important to be aware of this and also to be as transparent as possible about our assumptions. And again, like I said several times now, causal networks is really just a very simple tool just for yourself to make yourself aware of your assumptions, or also the readers of your publications. Oh, sorry. And then causal networks, they really help to identify where information is propagating. Again, it's when you have information propagating, when you have, or you expect correlations, when you have these open paths in the network, and to really extract the causal effect of interest, which is often just the same as blocking the open path on the network, or to condition on the confounding factors. Again, important, causal inference is not a method, but it's really a framework which helps to make you these choices, but it's fully non-parametric. So how you then quantify effects using linear regression or other methods, it's up to you. And I also think also what we try to argue in this BUMPS paper, which I referenced here a lot, is really that usually I think it involves really small changes to your scientific practice. So we already use linear regression, for instance, all the time, or these different categories of data. So it really involves small changes in scientific practice, but I think it really allows you to draw stronger or causal statements, which is often not the case. I actually promised an outlook on causal discovery. I won't do this here. I will just say that there exists this discipline of causal discovery, of learning causal structure. So again, and what I talked here about is that we have this causal model or this causal network, and then we use or based on this network, we quantify causal effects. But there's also this discipline that one starts with time series data and one wants to learn the causal network. So input is time series data representing different mechanisms, and the output is this causal network. And this can be achieved through so-called causal discovery algorithms. for example, the PCMCI algorithm, which have been designed to also, to be particularly designed for time series data. It's really based on within this philosophy of causal inference. So, for example, to decide whether there's a causal effect or a causal link in the network from X to Y involving some lag, in this case tau, one would iterate through different combinations of conditions. So one does the same thing. One does this in an optimized way, and this way to kind of identify the spurious correlations, which, for example, can emerge due to common drivers or mediators, or in this case, autocorrelation effects. Again, there are a lot of papers and references already, but it's the same philosophy, but it's a bit involving more assumptions and or addressing a different task. But again, here also the important part is really that application of this algorithm, they also require process understanding. So you also have to bring some expert knowledge in to, for example, choose the relevant time series and processes which make sense for your task. And this is just some papers where this causal discovery algorithms have been applied. So this is the very last slide, I promise, but I just wanted to advertise a special collection atmospheric science letters, which is on generally data science approaches to evaluate weather and climate extremes. And it's a special collection which is particular dedicated to early career researchers. I'm an editor of this special collection, so is Aglaé, who is giving the next talk, and then also Zach Leib and Danielle Thumer. They're also guest editors, so if you're interested in submitting your work or you have questions about, you can just reach out to us and ask us. Otherwise, we hope you submit your work there. And well, I think time is pretty much over, so just say thank you for your attention. I hope you enjoyed the lectures and the practicals. I hope you consider including causal networks in your analysis, and well, if there are questions, we can maybe discuss now, and otherwise you can also reach out to me, and I try to answer your questions then.
Okay, thanks. There was a question on the backdoor criterion, but Ellen has answered it, so I think that's fine. Are there any other questions from anybody? I will say that although it's a small change in practice, it's a large change in philosophy, and not everybody gets it. It sort of gets into the whole question of what is objectivity, which Aglaé may actually talk about in the next lecture, the whole question of objectivity in science, but at least you have a sympathetic set of editors in that special issue. So it's take advantage of it. Oh, the question from Rosa, I think that's Judea Pearl, who was actually did a lot to advance machine learning methods, but then turned out to be also extremely critical.
Yeah, he's basically the founder of Bayesian networks, and you will also see that Bayesian networks are, well, in a way the same as a causal network, only that it does not involve this cause interpretation of links. But a causal network is also a Bayesian network.
Okay, I think we should, so with apologies to Aglaé, we'll just take a short 5-minute break now, and we'll start you at 5 past.